You've no doubt noticed that as we solve systems of linear equations, right, when we do row reduction to get to the row echelon or reduced row echelon form for a matrix, we end up with these leading ones, and how many of these leading ones there are really goes a lot towards determining what the form of the collection of solutions looks like. So the position and how many of these leading ones there are, that's something worth keeping track of. So for that reason, we're going to make a definition. We're going to call the number of leading ones in the row echelon form of a matrix the rank of that matrix. This is well defined because every row echelon form of a given matrix has the same number of leading ones. We've proved that, and actually we proved even more that there's a unique reduced row echelon form for any matrix A. And so you can take the rank of A to be the number of leading ones in that reduced row echelon form. So just to get a hang for this definition, let's calculate the rank of some matrices. So let's start with this one, A, find the rank of this. So all we need to do is, go through the usual process of row reducing to get to a row echelon or reduced row echelon form. So we'd start out, I guess, by dividing the first row by 2, so that's going to give us 1 and minus a half and 3 over 2. And then the rest of these rows aren't going to change. 3, 4, 2, minus 5, minus 14, 0. And, continue with the process of row reduction. So you're going to have row 2 minus 3 times row 1, and row 3 plus 5 times row 1, and so on. By no doubt, by this time in the class, you've solved enough systems using row reduction that you're tired of doing it, and I wouldn't blame you for being tired of doing it. It is pretty tedious. It's kind of nice in that it's a set process that will always get you a solution, but it's not very exciting to do. And for that reason, we can use a computer to do it, right? Computers are exactly the tools to use when there's some calculation that is a very set process, but is too big and tedious to want to do yourself. So let's make a computer do this. So I have a tool here that we can use to generate the reduced row echelon form of a matrix. So right now it's displaying the reduced row echelon form of this matrix. So the way that we have to enter this, so this is called Sage Math. Sage is a mathematics package that's built on open source technologies, and it's pretty programmerly, so you have to be willing to deal with sort of programmer ways of entering things. Matrices are entered row by row, so the square bracket indicates that we're going to be entering a matrix. The second square bracket says this is the first row, so 1, 1, 3 is the first row, and then close the first bracket, that means that's the end of the first row, and then comma to enter the next row, and so on. So for our matrix, I'm going to be flipping back and forth between the windows here. So 2, minus 1, 3, and then 3, 4, 2. And then last row is minus 5, minus 14, and 0. Okay. And then we can just hit evaluate. Boom. There's the reduced row echelon form for this matrix. So it's got 2 ones in it, 2 leading ones in it, and then some coefficients over here. So when we finish this row reduction, if we did the whole calculation, we'd end up with 1, 1, 0's here, 0 here, and then some non-zero value here and here. Right? Our reduced row echelon calculator told us what these numbers were, but to know the rank of this matrix, all we need to know is where the leading ones are. There are 2 of them, so the rank of this matrix A is 2. All right. What about B? So B is a different size, but we can still use the reduced row echelon calculator. So 3, 2, 1, So we aren't going to need a third row, so we'll delete this third row. So first row was what, 3, 2, 1, and then -6, -4, -2. All right, and in this reduced row echelon form, there's just that one leading one there. So this reduces to a matrix that looks like there's a leading one here, and then some entries here. So I've put stars here. I think over here I said non-zero. It's true that these entries are non-zero, but it doesn't actually matter if they're 0 or non-zero. All that matters is they're to the right of a leading one. And then, let's see, it was all zeros like this. So this reduced row echelon form only has one leading one, and so the rank of B is 1. Okay, so let's do this last one, the rank of C. So 1 minus 2, 1. 1 minus 2, 1. 2, sorry, minus 2, 1, 2, minus 2. And then now we have a third row again. Third row is 1, 2, 3. Okay. So the row echelon form of this one is like this, 1, 1, 1. And then, in fact, there are zeros here above this diagonal of 1s. It wouldn't matter if there were zeros here or not. All we need to know is that there are 3 leading ones. And so the rank of C is 3. All right. So the rank actually has, the number of leading ones, when you write down the collection of solutions for a system, the number of leading ones and the number of columns that don't have a leading one, those sort of have this interplay to determine how many free variables there are. So let's look into that. So what we're going to do is suppose that these matrices represent a homogeneous system of equations. And we're going to see if you compare the rank of a matrix, the rank of each of these to the structure of the collection of solutions. We're just going to see what happens. So for this first one, it's already in reduced row echelon form, so we can write down the rank immediately. The rank of this matrix is 2 because there's 2 leading ones. Okay, and if we write down the collection of solutions for the homogeneous system that this represents, so if we call the variables maybe x, y, z, and w in our usual way. So the first row tells us that x is minus 2z, and the second row says that y is minus w. Okay, so there are 2 free variables here, right? We had 4 variables. The rank was 2, and there are 2 free variables. Okay, let's look at our second example. So again, we're treating these as if they're representing homogeneous systems. So 4 columns, so we need 4 variables, x, y, z, w. The rank of this, again, this time there's 3 leading ones, so the rank of this is 3. The first equation tells us that x has to be 0. The second equation says that y has to be minus 2z. And the third equation says that w has to be 0. So here there's 4 variables. The rank was 3. and there's one free variable. All right, one final example. So this matrix has rank 2, clearly. There's 2. It's in reduced row echelon form, so we can just count up the leading ones, and there's 2 of them. Since there are only 2 columns, there are only 2 variables, so x and y. X, well, so this first row says that x has to be 0 if we're treating this as representing a homogeneous system. The second row says that y has to be also 0. So here we have 2 variables. The rank is 2. And the number of free variables is 0. All right, so looking at these 3 examples, right, there's a pattern here, right? The free variables and the rank always add up to the total number of variables, right? That's true for all of these. So that makes you wonder, well, is that always true? Let's see. So if we have an m by n matrix, and its rank is, let's call the rank r. Okay, we have n variables. Right? If this matrix is representing a homogeneous system, that homogeneous system would have n variables because the number of variables is the same as the number of columns in the matrix. And it has it has r leading ones. But each leading one, right, and what happens when you have a leading one, that determines one of the variables. So a leading one means that the variable corresponding to that column is not free. So a rank of r, that means r variables that are not free. And if there are r variables that are not free, then that means that all the rest of the variables must be free. So there must be n minus r variables that are free. So just by keeping track of the position of these, or the number of these leading ones and the number of columns, we can actually tell just from the rank and the size of the matrix, we can tell how many free variables there will be in the collection of solutions for the homogeneous system corresponding to the matrix. That's pretty amazing.